Hello guys, this is Paul McWhorter with TalkTechBoy.com, and we're here today with episode number 90 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, hopefully most of you guys already have your gear, but if you don't, look down in the description. There is a link over to Amazon. You can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what we're going to do is we're going to start learning more about the Raspberry Pi Pico W PIO state machines. That is the programmable input-output state machines. And these are very powerful little devices that we're starting to become comfortable with. I think we've done maybe 3-4 lessons on them already. And we've only looked at, right in the state machine, there's a total of 8 commands. And we've only looked at maybe 2 or 3 of those commands. And so we're going to learn some new commands today so that the state machine becomes even more powerful for us. Does that sound good? I hope it does. Let me get out of your way, and then let's come over here and let's look. Just want to remind you the circuit that we're going to be working with. We have 4 LEDs. Ignore these buttons. These buttons are for a future lesson on the state machine. But we have these 4 LED. The rightmost, the least significant bit LED, the long leg is connected to GPIO pin 16. And this one is 17, 18, 19. The short leg of each LED goes through a 220 ohm resistor down to ground, and then the long leg is connected to the corresponding GPIO pins. Okay, so what are we going to learn today? We're going to learn about timing, we're going to learn about looping, and we're going to learn about shifting. Okay, so far, everything has been going so fast that we had to kind of slow it down on the Python side by interacting with those TX-RX registers and having some commands on Python side to slow things down. But if you really want to take full advantage of your state machines, you want to push everything possible over to the state machines and not have the Python main program doing hardly anything at all. And so that's what we're going to be looking at, is how we can control the timing on the state machine itself. Also, we're going to be looking at looping. So far, we've just had one loop. That's that wrap that you put wrap and you go to wrap target and you just go every single time from wrap to wrap target. You loop forever and no real ability to have any type of even crude conditional on that. So we're going to be looking at some looping and some jumping, and then also we're going to be looking at some shifting. Like before, what we've done so far is we take the contents of X and we'll put it in the ISR, or we'll take the contents of Y and put it in X. But what we're going to look at today is, instead of just grabbing some bits and putting the bit somewhere, what we can do is we can begin to shift. Certain registers allow us to shift into them or shift out of them. So we're going to be looking a little bit more at shifting today. Sound good? I hope it does. So let's come over here and let's just start coding. Okay, let's see what we can do. And I think I need to create a new program here. There we go. Okay, so what is the first thing we want to do? Well, let's just see if we can begin to control those LED a little bit. We want to control those LED a little bit. So what I'm going to do is I'm going to put import RP2. That is our library for accessing the state machine. I'm going to import time. I really don't think I'll use time, but I might, so I'll just put it in. Then from machine import pin. Why? Because we are using those GPIO pins, so we need to have pin from machine. Now we are going to put Python on notice that it's fixing to get some assembly language code for the state machine. So what do? The at decorator tells MicroPython that incoming assembly language code for the state machine. So we're going to go rp2.asm_PIO, and then we're going to say the out init is equal to, and it's going to be rp2.pio.out_low. What are we saying? Before the state machine runs, we want to initialize all the LED to 0. Well, if I just did this, it would initialize the first LED to 0. So if I want to do all of them, I have to have this awkward trailing comma, and then I've got to say times 4 pins. So whatever pin I start with, I'm going to set to low, and then the next 4 pins, the next sequential 4 pins are also going to be set low. And then we also need to be telling it what direction we are shifting, and so I can say out_shift shift direction dir is equal to rp2.pio.shift_right. You should be very familiar with after the number of lessons we've done. So Python has been put on notice that incoming assembly code, so we need to give it that function. So I'm going to call it PIO define PIO PROG like that. Okay, put a colon, and now what I'm going to do is I'm going to put in my wrap colon, not quote. Okay, those are adjacent keys on the keyboard, and it doesn't count if you catch it before you run it. Okay, so I'm going to put in my wrap target like that. If I'm going to put in my wrap target, I'm going to go ahead and put in my wrap just so I don't forget it. So now here is the juicy goodness of our code is going to start here. And so what I'm going to do is I'm going to just start by setting X, the X scratch register. I'm going to set that to 0B01 or 0B 0B1010. 0B just says that I'm going to send it bits. And what bits am I going to send it? I'm going to send it 4 bits. I'm going to send it bit 1, bit 0, bit 1, bit 0. Okay, that's pretty straightforward. And then what I want to do is I'm just going to go ahead and I'm going to move to the pins what is in, I'm going to move to the pins what is in X. So the data that's in the X scratch register is going to be moved to the pins. Let's just go ahead and take care of some stuff down here. And so I'm going to go ahead and instantiate the state machine. SM0, I will call it, just because that is my habit. RP2, the library dot state machine, the method. What state machine do I want to fire up? State machine 0. I should do state machine 1 once just for fun. PROG. And then I'm going to say out underscore base. What is the base pin that I'm going to start with? That is going to be equal to pin 16. Why? Because that's how I hook the circuit up. And since I said 4 pins, it's going to start at 16 and it's going to use pins 16, 17, 18, 19. So now my code matches the circuit that I built. That looks good. I like that. Now what I'm going to do is I'm going to say sm0.active and I'm going to turn it on. So you see, this is what I'm trying to get towards. You see, in Python, really all I'm doing is just firing up the state machine and all the real work is going on down on the state machine. So somebody tell me what is going to happen if I run this thing now. Hopefully I haven't made a mistake already, but if I'm going to run this thing, what is going to happen? Hold your breath. Okay, and I got an unexpected result. Why did that not work? Okay. Why did that not work? I set X to 0B1010. I move X 2 pins. Okay, I have out and knit. I have the base pin set up. Man, that looks so right. It looks so right. 0 PIO G out base pin 16. It looks so right. You have to put a 1 there to turn it on. That scared me a little bit. That one scared me a little bit. Okay, hold your breath. Okay, boom. What happened? I put 1010 in the X register, and then I move the X register to the pins, and I get a 1010. Okay, that is pretty cool, isn't it? Well, now let's see if we can get a little going back and forth thing going here. So I'm going to say set, and this time I'm going to say X is 0B, and then I'm going to go 0101. So I go from 1010 to 0101. Okay, and so what should I see? I should see it go 1010, 0101, and I should see it blink like that. And so let's go ahead and let's run this. And when we do, did I not? Let's click it. Okay, there it goes. What did I do? I set it, but I didn't move it. So move X to the pins. I guess I should say move to the pins from X. Move to the pins from X. Okay, now let's run it and let's see what happens. Okay, an unexpected result. I have all 4 LEDs on. Someone tell me why I have all 4 LEDs on instead of seeing it go like, like back and forth between 1010 and 0101. Someone tell me, leave a comment down below. Comment in the live chat if you are catching this on the premiere. Okay, this is why. How fast does the state machine run? By default, the state machine does 10 million operations a second. So this blinking is happening at like a 1/10 of a microsecond. A 1/10 of a microsecond. Hate to tell you, you might be young and sharp and healthy, but you're not going to be able to see that with your eyes. So we're going to have to slow it down. So if you notice, I left out the command here to set the frequency. And sometimes when you do that, you get unexpected results because this thing's running so fast. It says, this thing isn't working. Well, yeah, it's just working really fast, so fast you can't see it. So why don't we go ahead and set the frequency to about the slowest you can, which is 2000. Okay, and now let's come in and run this. So we run it. Doesn't like line 12. What is that nonsense? Comma. There's the comma. Okay, now let's run it. And again, what we are seeing now is it just looks like that they are constantly on. Now let's think about this. At 2000 hertz, that would be each operation is a half of a millisecond. Sorry, guys, your eyes cannot see a half a millisecond changing signal either. So what is our problem? Our problem is we need to slow it down even further. Now, what you can see is this command here, that takes 1 clock cycle. Well, what I'm going to tell it to do after that, I'm going to tell it to chill for 31 clock cycles. Okay, it's going to chill for 31 clock cycles. So it's going to set X in 1 clock cycle, and then it's going to sit there 31 more clock cycles. Well, if I can do that too, that's not good. If I can do that too, and the spacing doesn't really matter. If I can do that too, the set, let's do it to the move as well. You can't do this on all things, like I think label and a few things like that. You can't put the, you can't put the sit and chill command or the sit and chill parameter there. But I should be able to put it here, 31, okay, and then I should be able to put it here. And then wrap and wrap target are not real commands. They're just sort of an automatic free loop that you get. And so I think this is about all that we can do. And so now this time let's do it. Okay, look at that. Okay, you can see that. It's so fast that you can't see it, but at least you see that it's blinking. You could not say, oh, that was 1010 going to a 0101. You couldn't see that. You couldn't say that. And so now what we need is we need to slow the program down further. Well, there is a command that does absolutely nothing, and that is called no-op, like that, nop, open, close, and then I'm just going to tell it to do a nop there, and then after I set the pins down here, I guess you would just want to kind of do it in the same place so that it will, you want to do it in the same place so that it'll kind of be blinking symmetrically. So let's do it after we do the move. Okay, so now I'm going to slow it down with a no-op. Okay, well, I've just, remember guys, we've got 32 lines of code. We got 32 instructions that we have to work with, so we don't want to waste any. So it would be kind of silly for me to put in 100 no-ops, but what it would be better is if that no-op that just cost me 1 instructions, I then chill for 31. Okay, and now I can copy this, and then I also need to do it on the other side, like that. All right. Okay, now see if we can notice a difference yet. All right. Yeah, I can see you're starting to see it blink more. Well, what do we need? We need more no-ops, okay? So let's say we put a total of 4 on each side. That's 1, 2, 3, 4. And that was some really poor pasting that I did there. And even though I saw it was doing that, I just kept doing it, which was kind of even more silly. Okay, so I have 1, 2, 3, 4. Let's just copy all 4 of those like that, and then I will replace this one with a 4. And so now I have 4 and 4. So let's come up and let's do this. Now I think that I can almost see that it's going from 1010 to 0101. But I think I'm going to take 4 more on each side. Okay, so I'm going to put Control V. And then I'm going to put Control V. Okay, now let's run it. Okay, now do you see more clearly what's happening? And that's 8. Well, let's see if we do 12 on a side. And right, each one is giving me 32. Each no-op is giving me the no-op and 31 weights. So it's like 32 clock cycles that I'm burning to try to slow this bad boy down. So that's 12, and then I need to paste it down here as well. Get another 12. All right, so now let's run it. Okay, now do you see how it's slowing down where I can see it more comfortably? Okay, what's going to happen if I do Control V? And then what if I do Control V? And now let's try that, and let's try that. And I get an ENOMEM error number 12. What do you think happened? Like a mem error? Huh. How many lines of code? How many instructions do I have? 32. And I think I put, what was it, like 12 here? And, or no, it's maybe, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I put 16. I put 16 here and 16 here. That's 32. And I still have 1, 2, 3, 4 commands. I don't think the wrap target counts, so I have 4 commands too many. So 4 instructions too many. So let's steal 2 from the top side, and let's steal 2 from the bottom side, and then let's run this thing, and it runs. And so this is kind of like, using the tools that I'm showing you right here, this is about as slow as you can go, but it's slow enough to track what's going on. And so that is pretty neat. And what have you learned? You've learned how to begin to try to control. You've learned how to begin to try to control the timing of your program using no ops. Now we could actually calculate what is it that each operation at 2000 hertz is half a millisecond. And so right here, this would be 32 half milliseconds. And so that would be 16 milliseconds that this is going to burn right here. So we can actually go in and start counting our timing very, very precisely. Well, you might say 16 milliseconds isn't that small of a number. That's true, but then don't do it 31 times. If we only did it one time, it would burn half a milliseconds. And then if we came back and set this at 10 million, then we would have what? Precision of 0.1 or 0.5 microseconds. Okay, we would have precision. No, it's 0.1 microseconds. I said it right the first time. 0.1 microseconds precision control of timing. And that's really important if we're developing communication protocols, or we're having our device talk to another device, or all types of different things. You want that very precise timing. And so it's good that we can get it, and you can see here how you can control the timing. You can see here how you can control the timing. So that is kind of the first thing that we learned today. We learned a little bit about controlling the timing. Okay, let's go to our next one. Let's go to the next thing that we are going to do. And what we're going to do here is I'm going to show you that I've told you that there's 8 commands, but those commands have certain parameters. And if you use those parameters, you can almost turn that command into a different command. If you use those parameters, you can get, like, you can squeeze out a new thing that you can do. Okay, so I think that I have I'm trying to think, I have sort of the same type of program. Okay, I've got the same type of program. Let's see. Well, what I need to do is, okay, so this is what I'm going to do. I'm going to leave the program the same, but just to show you, I'm going to go 1, 1, 1, 0. And then down here, I'm going to go 0, 0, 0, 1. And I'm going to leave it running at that same rate. And so let's come in and let's see. Okay, it's 1, 1, 1, 0, and then 0, 0, 0, 1, like that. Okay. I think that is a pretty good way. That is a pretty good way to do it. But I think down here, I really need to make it. I need to make this 0, 1, 0, 1, so that I'm going to show you something, but for you to see it, I've got to select this. So the second one now is 0, 1, 0, 1. So let's run that. Okay. Do you see this is 1, 1, 1, 0. And then we come down here and it's 0, 0, 1, 0, 1. It's kind of hard. You see, it's still going fast enough that that's a little bit hard to see, but we are getting exactly what we put in. So that is good. Now, let me show you, we are so starved for instructions. Let me show you one kind of neat thing you can do. I can take that B that I put in, I can take that bits of 1, 1, 1, 0, and when I move it to the pins, on the way to the pins, I can invert it. Okay, on the way to the pins, I can invert it. Now, in X, I haven't changed X. I take it out of X, I invert it on the way to pins. So if we came back later and looked at X, X is still what it is, but it doesn't take X. It takes the invert of X and put it on the pins. And same thing here, I can invert that X and I can put that on the pins. And so you guys tell me what this is going to do. Leave a comment down below before I run it. Leave a comment down below. All right, or leave a comment in the live chat if you're catching this as a premiere. Okay, let's run it and look at what happens. And let's see. What you can see is it changed it from a 1110 to a 0001, right? Watch it. You see it's a 0001. And then also it changed it from a 0101 to a 1010. Okay, so what did I do? I inverted those bits. I opposited them. I opposited the bits. And as you're getting down working at those bit levels, and you're down here where you only have 8 commands, you might need to come back at some point to this invert command to do something that you would want to do. Okay, so that is a very powerful, even though you might not see it now, it is a very powerful option to let us do neat and interesting things. Okay, let's look at something else now. All right, what I'm going to show you is how you can double a number. Like you'd say, I know how to do that, times 2. Well, the state machine don't got no times 2. You know, there's no, I hate to tell you, there's no add, there's no subtract, there's no multiply, there's no divide. And so if you needed to multiply by 2, how could you multiply by 2? Well, let's make this a little more fun. Okay, so what I'm going to do is, instead of setting it here, what I'm going to do is I'm going to pull it from the TX, I'm going to pull it from the TX FIFO. If I'm going to pull it from the TX FIFO, then down here, what I'm going to need to do is I'm going to need to put a let's make it a while true. When it's true, true is always true. So I'm going to do that. And then I'm just going to go ahead, I'm going to get input from user, x is equal to int, and then what input, enter your number, like that. And then I'm going to put that sm0 dot put. What am I going to put? I'm going to put x. So x is now going to go to the TX register. And yeah, I've been talking about, oh, you want to do everything in the state machine. Well, yeah, I have to, in this case, pass it the number so it can do the operation on it. So I do, it's legitimate for me to do that here. So now after I put it, I'm going to say x is equal to sm0.get. Let me go ahead. I got the number, so I'm going to print it. I'm going to say print, and I'm going to say your number is, and then I'm going to also put just print x. So what I just input, I'm going to give it back to the person. Then I'm going to put it to the TX register, and then I'm going to get it from the RX register. So I put it out to the state machine. The state machine's going to chew on it. The state machine's going to put its result into my RX FIFO, and then I'm going to get the number from the RX FIFO, and then I'm going to say print your number doubled is like that, and then comma, and then it's x again. Okay, how does that look? Okay, so let's look here. So I'm promising to double it, so I guess I better double it. You know, I think even I bet I don't have to have all these no ops. Okay, I bet I don't have all these no ops, because why? Because now the timing's being done in that, you know, in that wait for the input. All right, so let's see if it works like that. You see, there's not a reason for me to slow it down because it can't go faster than I input the data. All right, now what did I do? We kind of got this cleaned up. So what I did is I pulled. Okay, now what I'm going to do is that number that I pulled into the output shift register, now I'm going to move that to X from the OSR, right? So that number I put in, where is it now? It is in X. Now I'm going to set y. I'm going to set y to the number 1. I'm going to set y to the number 0. Okay, I've set y to the number 0. Okay, now that number, now I know why I needed it, but the reason is I was originally thinking about displaying the original number here and then displaying the doubled number here, but we'll just look at the doubled number down in the serial monitor because I don't want to put all those no-ops back in. So I'm going to set y to 0, and I've set x to what I sent in from the main Python program. And now what I'm going to do is I still got this invert, which I don't want to do that business anymore because I'm doing something completely different. But what I'm going to do is I am going to now move how do I want to do that? Yeah, I want to move to the ISR, the input shift register, from X. Okay. So this kind of makes sense. I pull the number into the output shift register. I move the output shift register to X. And then I move X to the input shift register. Okay? And now I am not going to do any of this other setting here. I just didn't want to write the whole code again. So let's just summarize where we are. I'm pulling into OSR. I'm moving from OSR to X, and then I'm moving from X to ISR. And then what I am going to do is I'm not going to put it out there to the pins. I'll put the last one to the pins. I'll put the answer to the pins. Okay. So now X is in my ISR. Well, this is the magic command. I can do an N underscore. And what this does is it pulls something into the ISR. N is a special command for the ISR. So I don't need to specify ISR. N underscore is just saying pull something into ISR. Well, what do I want to do? I want to pull Y. And how much of Y do I want to pull in? I want to pull in 1 bit. So what would that pull in? It would pull in the least significant bit of Y. Well, if I'm going to do that, I better set Y. Okay, so I'm going to set Y. And what am I going to set Y to? 0B 0 0 0 0. Okay, so now what is this N going to do? It's going to pull this 0 into ISR, and everything that is in ISR will shift in the significant direction. So whatever is in ISR, everything will shift 1 bit this direction, and then this empty bit is filled by the first, which is the least significant bit of Y. So I'm going to pull this Y into, I'm going to pull this Y into ISR, and what was in ISR is going to scoot to the left. Now, if you think about your binary, if I have 0 0 0 1 and I shift everything to the left, I've got 0 0 1 0, which is a what? A 2. If I have 0 0 1 0 and shift everything to the left, I get a 0 1 0 0, which is a 4. And you can try it with whichever number you want, but shifting 1 bit to the left doubles. Shifting 1 bit to the left doubles your number. Okay, so now at this point, what do I have? ISR, the number in ISR has doubled. Okay, the number in ISR has doubled. Okay, so I move from, I set Y Okay, I think I'm thinking about this right. So I set y to this, and then I pulled into x. I moved x to ISR, and now from y I'm getting a 1, and then I'm going to move it to the pins, okay, and then I'm going to wrap. So let's just try this. So if I do this, I start with a 0, or I'm going to input it from the keyboard below. So let's see. Let's just see what happens. So I'm going to run it, and if I say input the number 1, it says your number is 1. And then I did not want to invert this because this was from our earlier program. Okay, and so now let me run this. Okay, and if I say 1, it doesn't like something. Let's see. Y is set to 0. I pull into X. I pull into OSR. OSR goes to X. X goes to ISR. I NY 1 bit. And now Y is where, from Y I do it. Now what I should have done was I should have moved ISR to pins, because ISR is what was just doubled. And then I'm going to wrap. And still there was a problem there, so it might be that I need to go ahead, and now that I have the ISR doubled, I move it to the pins, and then what I can also do is I can push it back out to this, which will then be gotten here. So let's try that. Okay, so enter your number. My number is 1. Okay, and then it says your number is 1. Your number doubled is 2, and then what do I get? I get out here the answer, the doubled number. So let's try it again. Let's say that what if we do a 4? Okay, then what if we do a 4? I've got a little bit of a timing problem here because what I'm doing is, in Python, I'm putting in getting before it's had time to go through the state machine. So let's say a time dot sleep of even like a 0.001, just any tiny little delay there should be able to do this. And so let's say I want to put in a 4. Okay, I get an 8. What if I want to put in a 5? I get a 10. What if I put in a 3? I get a 6. Okay, see, I've shown you a little technique here that since I don't have times 2, I can multiply by shifting to the left, if that makes sense. So that's a pretty cool feature here. And again, when you have very little things that you can do, every little thing that you can do will make your state machine more useful. Okay, let me show you something else. What if I wanted to double and add 1 to it? If I wanted to double and add 1 to it, well, again, we pull into OSR, we set Y to 0, we move OSR to X, and then we move X to ISR, and then we shift 1 bit from Y, so we shift a 0 into ISR, then we move ISR to pins, and then we're also going to push ISR. So that's what the program's doing. So now, what if I made this a 1? Okay, I make that a 1, and now I put a 3 in. I change that to a 1, and now I put a 3 in. Tell me what you think this is going to do. Well, what's it going to do? You shift to the left, that doubles it, but now into that blank position, you put a 1. It's going to times 2 and add 1. So if I put in 3, I am going to get a 7. 3 times 2 is 6 plus 1 is 7. So you see, I'm trying to show you how we can do some really crude math. We can do some really crude math in that state machine. Because once you get down in that state machine, there's some things that you're going to want to do. And you're going to want to do things more than just move from one register to another, or from your registers to your pins. You're going to want to do more than those simple things. And so here you got a picture of, okay, we can double, add 1. You could imagine that if you shifted twice, you could multiply something by 4. You could multiply something by 4 and add 1, or you could multiply something by 4 and add 2, or you could multiply something by 4 and add 3. Okay, so you see now you're starting to get kind of like more things that you can do. Okay, that is pretty good. So what have we talked about? We talked about timing, and now we have talked about inverting, and now we have talked about times twoing. So we've done timing, we've done inverting, and we've done times twoing. Now let's learn the one more thing that we are going to do today, and that is looping. Okay, right now you have this one infinite loop. It's almost like in Arduino, it's almost like the void loop. It's just there and it's looping. But what if you want a conditional loop? What if you want a conditional loop, okay? And I think what I'm going to do is I'm going to just start over, because editing the code sometimes is, I think, more confusing for you. All right, and I really regret taking out all those no-ops, because I'm going to have to put them back in this time. And then also we're going to go back to, let's see, I think that we are going to just go back to down here, not doing anything except just turning on the state machine is the only thing that we're going to do. Okay, so now let's come up here and we're going to learn how to loop, where you have a conditional loop. And what I'm going to be showing you is this is almost like making a for loop. It's almost like the world's crudest version of a for loop. But let's just say that I'm going to set, to get us started, x is going to be 0b1111. That's the number 15. So I'm going to set x to 15. Yeah, I'm going to set x to 15. And I'm going to want this program to run slow, so I'm going to let it chill for 31 cycles after the one clock cycle for the command. Then I'm going to chill for 31. And now this is what I'm going to do. I'm going to put a label in my program. My label is bit loop. You can call yours whatever you want. I'm going to call mine bit loop. I don't think on a label you can put the chill, because the label isn't really an operation. It's more like a pointer. Now what I'm going to do is I'm going to move the pins. I'm going to move to the pins what was in X. Okay, so if I just ran this now, I think I have enough that you should see the 1111. Okay, yeah. So you see I put it in and I moved it to the pins. Not very exciting. All right. Now what I want to do though is now I want to slow this thing down. So I'm going to go back to my no op and I'm going to do 31 no ops for the price of 1. And then I'm going to take this, copy it, paste it, copy those two, paste it. Now I have 4, copy. I have 8. Let's go ahead and do 16. Okay, I'm going to copy. I'm going to come here, 16. 16, let's see if we can go again. I think I can probably get that many. I want to slow down to where you can see it. So what did I do? I put a label up here, a label called bit loop. And so this line of code is called bit loop. Now, when we get down to the bottom here, what I want to do is I want to jump. And when I jump, where do I want to jump to? I want to jump to bit loop. And it will jump to bit loop when x is 0. When x is 0, it's going to jump to bit loop. And then what do I want to do when I jump? Like if I just did this, okay, if I just did this, it's going to be looping forever. Only instead of coming up to wrap target, it is going to come to bit loop. But it's going to do exactly the same thing because I haven't changed x, and so it's just going to be looping from here instead of looping from here. So let's run this and just make sure. Yeah, you see I've got 1, 1, 1, 1 because I'm just jumping back up to bit loop, and even though I'm kind of pausing here, nothing's changed, so there is nothing very exciting. And it loops forever. But I put where I wanted to jump to, but now I want to put a condition. I want to loop until x gets to 0. And every time that I get to this command, I want to x underscore decrement. So I want to decrement every time that I come here. I think I can probably get a 31 on here. Let that slow down a little bit. So now, every time I get here, I'm going to decrement x by 1. I started at 15, and every time I'm going to show x on the pins. You guys show me. Leave a comment. Say something in the live chat if you're at the premiere of what this thing's going to do. Okay, let's run it. Let's run it. Okay. Now look at that. Things are happening. Can you tell me what this is? If you look at it, can you tell me, is this just a random pattern, or is there something very specific that is happening here? This is a countdown binary timer, a countdown binary timer done completely on the state machine. Okay, let's look at it. Okay, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2. I can't count fast enough with it. But if you watch this, you can see that it is exactly and precisely counting down in binary from 15 to 0. And then after that, I drop out of the loop. I come to the wrap. The wrap takes me back up to the wrap target. And then I start over again at what? At 15. Does that make sense? I hope that makes sense. So what have we learned? What are other things you can do? I told you that it will just jump unconditionally to your target. If you take this out, that's going to jump unconditionally. What else can you do? What else can you do? You could put your counter in Y, and then you could decrement Y. Now, while you're decrementing and counting on Y is now you're kind of like your counter register. Inside of this loop, you could be playing around with X. Inside of this loop, you could be playing around in X. Okay, now let's see here. Are you guys ready for a homework? Are you guys ready for a homework? I think you are. Now pay attention. Pay attention. I think I am going to come over here. Okay, I'm going to show you this. And this is what your homework assignment is. First of all, I must say, in the homework assignment, the only Python code that you can have is you can turn on your state machine and you can instantiate your state machine, but everything has to be done in the assembly language in the state machine. Okay, everything has to be done in the assembly language in the state machine. And this is what you need to do. You need to create an up counter where you count from 0, 1, 2, 3, 4 on up. And this is going way, way, way too fast. So I want you to make your program count up from 0 to 15 as slow as possible. Okay. Now you might go in and say, I can put in 4 more no ops with 31s. Okay. But yeah, you can do that. Okay. But I want you to make the program run as slow as possible. And then really, I want you guys to post this to YouTube and then leave a link back to my solution. And then you leave a comment with a link. And then if for some reason it's not taking your link, then just leave a comment that says, hey, my homework solution is at my channel. And I can just click on your name and then get over to your homework assignment. Okay. But now this is what I want you to do. This program is what? Counting down, and I want you to count up, and this program is going much, much, much too fast. So let's see who can run this thing the slowest and have it count in the right direction. And so this is what I want you to see I did, just to give you kind of a stretch goal. Okay, so I come in here, it's at 0. I'll take a sip of coffee. It's at 0. It's at 1. Seems like I have it going pretty slow, doesn't it? 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it seems like about 8 seconds between each transition, and I am counting what? Up. Now, I have given you everything that you need to know in order to solve this problem. I've given you everything that you need to know in order to solve this problem. But now you have to think about it. And this is what the problem is. You have to think out of the box, and you have to think creatively. You have to think out of the box, and you have to think creatively, because you don't have that big boatload of Python commands. You have 8 commands, and with those 8 commands, I want you to create a 4-bit up counter where everything is done on the state machine. Okay, guys, I hope you are having as much fun taking this class as I am making it. If you enjoyed the video, give me a thumbs up, leave a comment down below. That also helps me with the YouTube juice. Subscribe to the channel and ring the bell so that you will get notifications when future lessons drop. And as always, I want to give a shout out to you guys that are standing with me on Patreon. Right now, it is the Patreon support that allows me to keep making these videos. So if you're enjoying them, think about hopping on over to Patreon and supporting this channel. And finally, and most importantly, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.